Okay, so today we will be considering, as I told you in the last part of yesterday's lecture, we will be considering parametric method of spectrum estimation, that is spectrum estimation by modeling. And I already told you the elementary ideas of modeling, that is you assume that the process is generated by passing a white sequence through a rational LTI system of transfer functions say z, which can be all pole, all 0 or pole 0 both, and therefore, the power spectral density of the received sequence would be nothing but mod square of h to the power j omega, h to the power j omega being the transfer function. So, mod h to the power j omega square into some constant, the constant denotes the input power spectral density. Now, input is white, so input power spectral density is flat, which is equal to some constant. So, in this case, the entire spectral density estimation boils down to identifying that model or estimating the parameters of those model, the coefficients that occur in the numerator and denominator polynomial in Z. Now, before I go further into that, I told you yesterday also that there is a justification for making this assumption and going by this method, and that comes from what is called Old's decomposition, a famous theorem by a great statistics person. His name is Old. It's called Old's This says that given any random sequence S n, you can always decompose it into two parts. Okay. One is x n, another is say z n, where x n is called non-deterministic part and this is called deterministic part. And these two are mutually uncorrelated. Okay. What is deterministic part? Zn also is a random sequence, Xn is a random sequence. Then if something is random, what is deterministic about it? That is a very, that is a kind of puzzling question. The Zn is random because it is coming from, it is basically originating from the given random sequence Sn. So, why do you call it deterministic? What is meant by a deterministic random sequence? Well, a random sequence is called deterministic if any current sample, say Zn, can be accurately given or is given directly by a linear combination of all its past sample, all or part of its past samples. That is, if Zn can be written as a linear combination of Zn minus 1, Zn minus 2, Zn minus 3 dot up to Z minus infinity. That is, if Zn is equal to some C1 times Zn minus 1 plus C2 times Zn minus 2 plus C3 times Zn minus 3 plus dot, then that means that from the entire past of that process Zn, I can accurately describe Zn without any error. Such kind of process is called deterministic process. To give you an example, suppose you take Zn to be a sinusoid of this form. Where A, the amplitude is random. Okay. Now, what is sin 2 pi by n into small n? It is a discrete sequence, which is sinusoidal sequence, which is periodic over a period capital N, and the amplitude A is A. So, every time you perform an experiment, you find this sinusoidal sequence, but the amplitude changes because amplitude is random. This process, according to me, is a deterministic random process. It is random because amplitude A is random. So, sometimes it can be very small, sometimes it can be very high. So, you get sinusoids of various amplitudes, in that sense it is random. But see, if you know all the samples of a particular Zn sequence belonging to a particular period, take one period of Zn and suppose you know all the samples, then you can accurately describe all other samples in terms of the samples taken over a period because of the periodicity. Because whatever you observe in one period, they only repeat. So, if you know all the samples within one period, then you can predict any future sample or past sample accurately without any error. Okay. Instead of this, you could also have a phase here, some phase, and that phase could be a random variable, or both amplitude and phase could be random variable, but still that does not take away the periodicity. So, if you still know the samples within a period, you know everything about the process. You know, I mean you know all the other samples of the process accurately. This kind of processes are called deterministic processes. If you take their spectral analysis, actually they give rise to what is called line spectra, that is just a series of impulses, Dirac delta functions or impulses in the frequency domain. Obviously, if you take a sinusoidal function like this, and if you take its autocorrelation function which is also sinusoidal, then take its Fourier transform DTFT, you will obviously get impulse functions, because any sinusoidal function, if Fourier transform gives rise to impulses. Okay. So, in general, this deterministic random part Zn, that gives rise to lines, that is impulses in the spectra. For the time being, we will not be considering this Zn. So, we will be concentrating now purely on x of n, that is which does not have any line spectra. What is xn? Xn is the purely non-deterministic part. That means, given any xn, you cannot write it exactly as a linear combination of all its past samples. That is, if you want to predict x of n from all its past samples as a linear combination, you cannot predict xn with 0 error. There will be some error of non-zero variance or non-zero power. Okay, there is some non-zero error. I mean, I won't say non-zero error, because error for a particular case could be 0, but that error will be random. So, its power variance, sometimes it could be 0, sometimes it could be non-zero, but the variance which is important, that variance will be non-zero. Okay. Such a process is called non-deterministic process, and for all the spectrum estimation by parametric modeling, parametric method, we will be concentrating on such non-deterministic part. I will not give you the proof of this whole decomposition, but I will consider this x of n. Now, since I am talking of prediction and all that, it is better that we again take resort to our previous previously described notion of this Hilbert space of random variables. Maybe to make life simple, we can assume all random variables, including the random sequences x n, to be 0 mean. So, Hilbert space of this is a set of, this is H, set of all possible random variables 0 mean. I am not writing 0 mean again and again, it is 0 mean. Okay. Then there is a rule of addition, that is for all x, y belonging to H, you know what is this x plus y, which is z belonging to H. It's called, we say that it's closed ended addition. What I mean by x plus y equal to z? It's the usual way we add two random variables to generate another random variable. But since I am considering the set of all possible random variables, the resulting variable, if you call it z, still belongs to H. So, if you add two elements of this H, the elements sometimes are called vectors. They are not like position vectors, but just by terminology they are called vectors. So, if you take any two vectors, that is any two random variables belong to H, there is a rule of addition involving the two, and what you get out of addition, that also still belongs to H. Similarly, there is a rule of scalar multiplication. If you take C, C could be a real or complex number. In fact, for our case, we will be assuming the associated field of numbers to be complex. So, C is any complex number, and C times x, if you call it say z prime, that also should belong to A. Okay. C is any complex number, and there is a rule of scalar multiplication in the usual way, like we know if x is a random variable and C is a scalar, what is C x? A second random variable. So, in each trial, whatever value x takes, that gets multiplied by C, and that is the value assigned to z prime for that particular trial. So, that is the physical meaning. Now, obviously, z prime also should belong to H, because H consists of all possible 0 mean random variables. Mean is always 0 in all these operations, and there exists a 0 random variable. Okay. 0 random variable, I put a bar here to indicate it is a vector. 0 random variable, it means it is such a random variable which always takes 0 value. Okay, we say that it takes 0 value with probability 1. When you add 0 to any x, what you should get back is x. That is the property of 0 vector. Then given any random variable x, there must exist is negative. There must exist given x, there exists, this is there exists say x prime element of H, so that x plus x prime is equal to this 0. In that case x prime is called, this means x prime is called actually negative of x, and we denote it by minus x. Obviously, x prime, what is x prime physically? Okay, whatever value x takes, negate that, that value is assigned to x prime. So, x prime is that kind of random variable. Okay. That is the physical minimum of 0. All rules of addition and scalar multiplication like associativity, distributivity, commutativity and all that, they work, they are valid here also. There is a definition of Hilbert space, like ordinary, like our conventional 3-dimensional vector spaces involving I vector, j vector, k vector. Here also we define something something called a dot product, which in a general sense is called inner product rather than dot product. So, for any x for x y belonging to H, we define the dot product like this is inner product, and we define it like this x y star, and x with x. Actually, there are certain basic properties that this inner product should follow. And those properties are satisfied. So, I will not go into that. I just define inner product, and if you take the inner product with itself, it gives you mod x square variance. That those properties are simple. E of x comma y should be conjugate of y comma x, that is satisfied here. E x y star is E y x whole conjugate, E y star x star whole conjugate. Okay. So, this is actually, this should y x star, this is one property. X with x must be real, greater than equal to 0, equal to 0 if x is the 0 vector, only then. If x is not the 0 vector, even if it takes 0 value sometimes, but on some other occasions it does not take 0 value, then mod x square can never be, expected value of mod x square can never be exactly 0. Okay. So, it is 0 only if x is a 0 random variable of that Hilbert space, otherwise not. Okay. And the other thing is C x y should be C times x comma y, that is easily satisfied. If here instead of x you call it C x, C can be brought out. Okay. And then linearity x 1 plus x 2 comma y should be x 1 y plus x 2 y, that is again satisfied by this inner product, by this correlation definition. If instead of x, if you put x 1 plus x 2 within bracket times y star, you can break it up and you can write in this form. So, all these conditions are satisfied. If two vectors, if x y that is equal to E x y star 0, then we say x and y are orthogonal. Okay. That is, in this case they are uncorrelated also. So, if two random variables are uncorrelated, to 0 mean random variables are uncorrelated, they are orthogonal. Okay. A set of vectors, say finite set of vectors will be linearly independent if no vector can be written as a linear combination of the others. Okay. If that is, suppose you are given two vectors, three vectors x 1, x 2, x 3, there is 3 random variables. If you cannot write x 1 as a linear combination of x 2 and x 3, or x 2 as a linear combination of x 1 and x 3, or x 3 as a linear combination of x 1 and x 2, then this is a linearly independent set. Okay. If it is not, if any of them is linearly expressible as a linear combination of the other two, that means this is redundant. So, this can be thrown away, other two can be kept, and again you examine the linear independence of those two and so on and so forth. You can reduce the set to a smaller set, where the smaller set is linearly independent. We all know this because we have discussed all this earlier, so I will not go too much into it. Okay. Then suppose you consider just a set x 1, x 2 dot 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 dot, the set can be infinite. Okay, set S. Then linear manifold is actually we also call span of S. It means set of all possible linear, that is I would say finite linear combinations Actually, we do not need all this, but I am just taking this opportunity to introduce few basic notions to you people. Finite linear set of all possible finite linear combinations of the elements of S. That is, what is this linear manifold of S? That is, it can consist of all the variables x 1, x 2, x 3 dot dot dot, then maybe C 1 x 1 plus C 2 x 2 or C 2 x 2 plus C 3 x 3. There is linear combinations involving 2 variables, linear combinations involving 3 variables, linear combinations involving 4 variables, set up all such finite linear combinations. That is called linear manifold. That is a vector space. It is because if you take any two elements of that linear manifold, one is one linear combination, another is another linear combination. You add the two, you get another finite linear combination. So, it is closed, is not it? So, you still remain within the linear manifold, because linear manifold consists of set of all possible finite linear combinations. If you take one entry of linear, one element of the linear manifold, which is some linear combination of these elements, and take another element of this linear manifold, which is again another linear combination of the elements of S, and then add the two, resulting thing also is a linear combination of the elements, some linear combination, some new linear combination of the elements of S. So, it also belongs to linear manifold. So, linear manifold is a vector space. Similarly, if you take any element of linear manifold, that is some linear combination, finite linear combination of the elements of S multiplied by a scalar, resulting thing is still a linear finite linear combination of the elements of S. So, again it belongs to linear manifold, so it is closed. So, you can verify all properties. Linear manifold is a vector space. Okay. It consists of 0 element, because it takes it linear manifold means set of all possible linear combinations of S means combination of the elements of S means each element of S also belongs to linear manifold. So, the 0 also belongs. Okay. Even if the 0 is not in S, you can multiply x 1 say by 0, scalar 0, you get 0, so on and so forth. Okay. Then, but remember, linear manifold never consists of any series, infinite series, that okay, x 1 plus x 2, C 1 x 1 plus C 2 x 2 plus C 3 x 3 plus C 4 x 4 dot 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 up to infinity. It only consists of finite linear combinations. But for dealing with these problems, we need to handle also things like series, infinite series involving x 1, x 2, x 3, x 4, like that. How to handle them? Okay. Suppose you have got a series like this, C I x I. C I is a sequence of scalars, and x I belong to S, say I equal to say 1 to infinity. Now, it is an infinite linear combination. Actually, it is not defined, it is not belonging to a linear manifold. Linear manifold consists of only finite linear combinations. The way we write is, we write it like this, some finite sums, S 1, you take C 1 x 1, S 2, take first two terms, C 1 x 1, C 2 x 2, S 3, that is C 1 x 1 plus C 2 x 2 plus C 3 x 3 dot 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 dot. You see S 1, S 2, S 3, they are all finite linear combinations of the elements of X. So, S 1, S 2, S 3, S 4, they all belong to linear manifold. Okay. And what is the limit of this sequence of S 1, S 2, S 3, S 4? That is what is given by this infinite summation, because from S 2 to S 3 when you go, we get one extra term, S 3 to S 4 another extra term. So, as I go towards infinity, I get all the terms of this infinite summation. Okay. So, that means this sequence S 1, S 2, S 3, each element here S 1 or S 2 or S 3 or S 4, each of them belongs to the linear manifold. Okay. Now, if the limit also belongs to the linear now S 1, S 2, S 3, S 4 dot dot dot, this sequence, each element belongs to linear manifold. Okay. Now, this its limit is, limit of this sequence is this infinite sum. Infinite sum is not part of linear manifold, because linear manifold consists only of finite combinations. Then what we say, we not only keep the linear manifold, we now want to expand it, we want to add some more variables or some more points to the linear manifold to make it bigger, and those points will be called the limit points. Limit points are what? I cannot give you all the details here, but just for mathematical correctness I am saying all this. Limit point means if you take any converging sequence, limit of any converging sequence in LM S. LM means linear manifold. This is LM S. That is, if you take a sequence in the linear manifold like S1, S2, S3, and it is giving that they are converging. That is, as it becomes bigger and bigger, S1, S2, S3, S4, S100, S million, S10 million. As you go further, what happens that you basically converge. That is, I mean, even if you add new terms, it is not changing much like that, it is converging. If that be so, then the limit of that converging sequence is called a limit point. Now, if we add all the limit points, that is append, not add, not addition, we append the set of all limit points to this linear manifold of S, then what we call, then it is called the closure of S, or you also call it the vector space of S, okay, the closure of S. That is, denoted like this, sorry, this is not closure. Okay, you can say closure, okay, fine. It is denoted like this, LM S, first linear manifold, and then put a bar, that is, take the closure of that. This is nothing but union, linear manifold of S, union limit points of LM of S. Then within this closure thing, we can write, you know, if we form any sequence, any converging sequence taking the elements of the LMS or even this closure of S, and the sequence, you know, it is an infinite, it is a like if we form an infinite sum, that is a series, we can happily write, we know what its meaning. That we can, given a series, we can always write in the form of partial sums like S1, S2, S3, S4 like that. That is a sequence, and since it is converging, we know its limit. Limit also must belong to this closure, because all the limit points are included in closure. So, we know what it means, it is now defined. So, just for mathematical correctness, I did so much. Now, I come back to that vector space issue, that is Hilbert space of random variable issue. We are now back to this random deterministic, non-deterministic random process x n. Okay. Suppose you want to project, you want to predict x n, what do you do? Like, you know, in a conventional vector space, suppose this is a vector v and this is one space, say u, you want to, you know, it's spanned by some vectors, you want to predict v in the best way from u. What you do? You take an orthogonal projection. So, this is your prediction, this is the original one, this is the error. Error is orthogonal to this plane or to this space u. Same philosophy works here. The theory for this I am not doing. What I am saying is this: suppose x n, as I told you, x n is purely non-deterministic. So, x n cannot be x n if this is like, you know, this is x n. This is x n. And this is the past of x n, that is, it consists of x n minus 1, x n minus 2, x minus 3, all the closure of that set. If you take a set, say S, or maybe past, if you call it past, is this set x n minus 2 dot, then you take linear manifold of that this set and closure of that. This is given by u here, okay. And you want to project, you want to obtain x n as a best possible linear combination of all the elements of this past, okay. So, you will have a best possible linear combination like maybe C I x n minus I equal to 1 to infinity. You see, it is an infinite sum, but there is no problem, it is perfectly defined, because I am taking the closure. There is, it is not only the linear manifold of this set, but it also includes all the limit points. So, this infinite sum is defined, and this must be the best, this coefficient should be chosen in the best way, so that this is the orthogonal projection, that is the, if you take the error between x n and this projection, you can call it x prime n, this part, this is x prime n, then the error E n, this error, the error is orthogonal to, you can say orthogonal to each element belonging to past, and therefore orthogonal to this closure of LM past. Okay. Only then this error is minimum in this variance. If it is not orthogonal, you know from geometry, if the error is not orthogonal, if the error were like this, suppose if the error were like this, and this much is your prediction, then the, of course, length of this is more than the length of this. So, error variance in this other case is much more. So, error is minimum only when, minimum in norm, minimum is variance only when it is orthogonal to the space on which the prediction is made. Okay. Same thing we will do here. We will assume that x n is now projected on the past, that is on this set L m linear manifold of past and closure of that, and the best prediction is x cap n given by summation of C I x n minus I equal to 1 to infinity. So, the error is minus x cap n. Okay. This error is E n. This is orthogonal. Remember, this is orthogonal, that is uncorrelated to, orthogonal to the entire past. So, it is uncorrelated, that is its inner product or dot product with x n minus 1 or x n minus 2 or x n minus 3, all the inner products are 0. So, it is orthogonal. Okay. Similarly, so x cap, similarly, I can do the same thing for x n minus 1, I can get, that is if I predict x n minus 1, if I try to predict x n minus 1 from the past that starts at x n minus 2, then x n minus 3, x n minus 4 and all that, I get another linear combination of those elements, that is my x cap n minus 1, and the error is now, we call it E n minus 1, that error is again orthogonal to, this error is orthogonal to what? Orthogonal to x n minus 2, x n minus 3, x n minus 4, like that. Okay. Now, remember one thing, if we know what is x, in the first equation, we know what is x cap n, C I x n minus I. Here, take out the first term C 1 x n minus 1. This x n minus 1 can be written as x cap, sorry, yeah, that was right. X n minus 1 can be written as E n minus 1 plus x cap n minus 1, and x cap n minus 1 is again a linear combination, maybe say d I x n minus I, but I will start at 2 to infinity. If you replace x n minus I by this, what you get? What you get is, you get one term involving E n minus 1 and the other term starting at x n minus 2, x n minus 3, x minus 4. Again x n minus 2 you replace by the same way, you will get a term involving E n minus 3, so on and so forth. So, that is, I am just cleaning up and explaining. If you take this first equation, x n, you take this on the left hand side is E n plus, so I take out the first term C 1 x n minus 1 plus the rest C I x n minus I equal to 2 to infinity, and then x n minus 1 again I write as some I equal to 2 to infinity, this is a projection, maybe some d I x n minus I plus the error E n minus 1 and plus the other term, this term. You see here you will have E n, then some coefficient times E n minus 1 and terms involving x n minus 2, x n minus 3, x n minus 4. One more step, x n minus 2 you project on its past, okay, and do the same exercise. You will get again terms like E n, then this right hand side will have E n, E 1 n, E n minus 1, E n minus 2 and terms like x n minus 3, x n minus 4, x n minus 5 like that, so on and so forth. So, essentially x n is given by what? If you do this exercise again and again, I hope you are understanding this. I just repeat briefly what I am doing. First I wrote this error E n as x n minus x cap n. X cap n was a linear combination of the past of x n. Out of that I pulled out x n minus 1. This x n and other terms are kept as it is. X n minus 1 again if you project on its past, the error is E n minus 1. So, x n minus 1 can be written as a summation of the error and that projection starts at x n minus 2. Okay. Now, if you simplify this, you will get one term involving E n, another term E n minus 1 and past x n minus 2, x n minus. You go on doing it again and again. So, you will keep getting terms like E n minus 1, E n minus 2, E n minus 3 and the linear combination. Only E n will have coefficient 1, others will have some non-zero coefficients. Okay. So, that means x n can be written like some linear combination of say H 0 E n, though H 0 is actually 1, then another H 1 E n minus 1, H 2 E n minus 2 plus dot 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 dot. I of course write H 0 is 1 as you have seen here, which is nothing but a convolution between the sequences H n, that is if you write H r E n minus r from 0 to infinity, as though the sequence E n has been passed through a causal linear time invariant system of impulse response H r or H n. Okay. Only thing is, you see E n we have seen is orthogonal, that is uncorrelated to all the past of x n. Therefore, E n is orthogonal to x n, x n minus 1, x n minus 2, so and so. Therefore, E n is also orthogonal to E n minus 1, because what is E n minus 1? E n minus 1 is an error between x n minus 1 and its past prediction. So, all the terms they are orthogonal to E n, therefore, E n is orthogonal to the difference between x n minus 1 and x cap n minus 1, that is we can write E n orthogonal to what? All the past. That means, I can also write E n is orthogonal to what? X n minus 1 minus its prediction, because prediction comes from further past n minus 2, n minus their linear combination. So, all the terms on this in this bracket involve x n minus 1, x n minus 2, x minus 3 like that. So, E n is orthogonal to each of them. So, E n is orthogonal to this error and this error is E n minus 1. And you can recursively apply this. E n minus 1 is orthogonal to E n minus 2, E n minus 2 is orthogonal to E n minus 3, so on and so forth. Orthogonal means uncorrelated. That means, E n is an uncorrelated sequence, which is also called white sequence. Of course, 0 mean, because the basic data from which they are generated, they are 0 mean. So, it is a 0 mean white sequence which is passed through a linear time invariant system. What kind of system? Causal infinite impulse response system, and that generates x n. That is the proof. So, any non-deterministic process x of n can be given directly as is always describable accurately as though it is generated by passing a white sequence, 0 mean white sequence through a causal IIR filter of impulse response as shown here by H n. Okay. This is very important. This gives rise to the idea of modeling, that in that case can I now approximate that infinite impulse response causal IIR filter by a rational model Hz, where Hz is a ratio of two polynomials in Z, numerator polynomial, denominator polynomial. If it is having both numerator and denominator polynomial, we call it ARMA or autoregressive moving average model, or equivalently pole zero model. Otherwise, we have got the autoregressive model, that is AR model, or we have the MA model, that is moving average model. In our case, we will be considering the AR model. So, now we have got a full justification for going for this modeling process. Okay. So, we will be assuming, we will be approximating that actual sequence H n, if you take its Z transform is approximately equal to 1 plus this is a pth order model I am taking, pth order model. This coefficient is 1. You know, it is a causal system. If you let z equal to infinity, this side becomes 0, and any causal transfer function, if you let z equal to infinity, what you get is H0, and H0 is 1, so that is why this is 1. Okay, this is basic DSP. For a causal transfer function Hz, if you let z tend to infinity, what happens? What is Hz? Summation Hn z to the power minus n, n starts at 0, goes up to infinity. So, H0 plus H1 z inverse plus H2 z inverse 2 plus dot 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 dot. Here, if you allow z to go to infinity, all terms disappear except for the first term, which is H0. So, what you get is H0. So, this expression, if you let z tend to infinity, all this A1 z inverse, A2 z inverse 2 and all that, they disappear, only 1 by 1 results, and it is 1 because H0 was 1, as we saw last in the previous slide, okay, in the previous page. So, if we can approximate this by choosing the model order P correctly, okay, and if the approximation is fair enough or good enough, then our problem is simply to estimate A1 to AP from the given data record of Xn, and that is the AR modeling problem. So, here what from now onwards what I will be doing, I will be assuming now that Xn has been generated by passing such a white sequence maybe En through a all pole system. So, in time domain, what does that equation mean? You have something like this. You remember what is the transfer function? 1 by 1 plus, that is xz by Ez. Ez is the z transform of the En, xz is the z transform of Xn, and this was dot 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 plus AP z inverse P. That means xz into this is equal to Ez into 1. In time domain, it means Xn plus A1 z inverse xz means A1 Xn minus 1 plus dot 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 AP Xn minus P is equal to this 1. It is not necessary that it should be 1, you can make it a coefficient B0 here, but I will make it 1 because even if you put B0, that B0 can be absorbed into En. B0 into En, you can call it E prime n. Only thing it will change is the variance of En. Since variance in either case is unknown, I will have these coefficients B0 absorbed in En, and you can call it E prime n, and why E prime n, again bring back the same notation En. So, that is why I can afford to maintain a constant 1 here. So, it is simply En, and En is what? En is orthogonal to, uncorrelated with all the past of Xn, and therefore, uncorrelated with Xn minus 1, Xn minus 2 up to Xn minus P. Now, given the data record of Xn, if I can find out A1 to AP, that is called AR modeling problem. Okay. Associated with this is also the interesting problem of linear prediction. Linear prediction, in the case of linear prediction, I do not care whether Xn is as a model or not. What I say is this: I want to project Xn into the space spanned by some finite number of past samples Xn minus 1 up to say Xn minus P. There is a vector space spanned by this, the set of all possible finite linear combinations. Of course, finite linear combinations because we have got only finite terms. That space, if you project it on this, that projection will be a linear combination, and the error is En. In that case, what is the error? This projection minus the linear combination for the projection. So, Xn minus that linear combination I write as I put a minus here just for convenience, x n minus I equal to 1 to p. This is the projection, this projection x cap n. So, what is E n? X n minus x cap n, which is minus minus plus, so it becomes equal to this. So, in the linear prediction problem also, the error E n is orthogonal to whom? To x n minus 1 up to x n minus p, not the entire past. In an air modeling problem, E n is orthogonal to the entire past, not just to x n minus 1 up to x n minus p, but to even terms further past. In the linear prediction problem, which is a defined problem from modeling, E n is just orthogonal to terms up from x n minus 1 up to x n minus p. But whether you are dealing with linear prediction problem or air modeling problem, I will be using only the orthogonality between E n and these few terms x n minus 1, x n minus 2 up to x n minus p. Since everything else is same, identical model equation and all, the two problems then turn out to be same. Okay, because I will not be using in the case of air modeling problem, even though E n is orthogonal to further past terms x n minus p minus 1, x n minus p minus 2 dot 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 dot, I will not be using them. I will be using only the orthogonality between E n and x n minus 1, x n minus 2 up to x n minus p, as I will be doing in the linear prediction problem also. So, both the problems will give rise to same set of equations, as we will see now, and those equations have to be solved. We know that E n is orthogonal, okay, to whom? X n minus 1 to x n minus p. So, what I do? I make use of the orthogonality. I know that x, I can write x n minus k to E star n. Okay. And by the way, if you permit me, I put a subscript p here, because if it is linear prediction, what is the order of the prediction? I am taking only p past terms. If it is an air modeling problem, what is the model of the, what is the order of the air model chosen? P. If instead of p, if it is p plus 1, because after all I do not know the exact model order. So, I could have also taken further some more terms and I would have got another order. So, whatever equation I have, the corresponding error and all, that would have been different there. Okay, the White's equation would have been different there. So, just to indicate that a pth order model problem or pth order linear prediction has been considered, I just put a subscript p in all these. Okay. And here also, or maybe I will do this little later, just a minute, I will do the same thing little later when further clarity will come. So, for the time being let it be like this, and if you take this, this is the inner product between x n minus k for k equal to of course 1 dot 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 p. So, x n minus 1 is star n, that must be 0, because that is what? Inner product x n minus 1 star n means actually E of E n x star n minus k star, which is nothing but inner product between E n and x n minus k and then star, and this E n is orthogonal to x n minus 1, x n minus 2 up to x n minus p. So, this is 0, conjugate of 0 is 0. So, this must be 0. Now, if I write it now, if instead of E n I substitute the left hand side here, what I get? E x n minus k into x n plus star, that is equal to 0. If you work it out, what will be getting? First term will be what? Okay, we start at k equal to 1 say, and then k equal to 2, then up to k equal to p, we will see some beautiful things. So, this is true for all k from k equal to 1 up to k equal to p. So, let us start with k equal to 1 case first, then k equal to 2, so on and so forth. So, for k equal to 1, first term will be what? X n minus 1 into x n conjugate, expected value of that is equal to what? R star I am putting the lag in the subscript r star minus 1. Why? You all know this, but still for your sake I am saying what is the first term? X star n x n minus 1, right, which also you can write as which you can also write as E of, I made a mistake there, x star n minus 1 star. So, it is actually not r minus 1 star, r 1 star. Am I correct? Or maybe, if you permit me, I rewrite the entire thing in a slightly different way, that is mathematically more convenient to handle. We have, because of the orthogonality, what you have, I write the orthogonality in the other way. In fact, that is a simpler way than what I did earlier. E of, sorry, orthogonality means I earlier wrote x n minus k. What I wrote earlier was x n minus k E star n, that was 0, but that also means that was actually roundabout. I can rather take E n here and x star n minus k, which is directly inner product, no conjugate anywhere, then that is equal to 0 for k equal to 1 dot 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 p. Now, if I put here this term x n then what I get for k equal to 1, what I get simply r 1. Then for k equal to 0, for k equal to 2, no sorry, for k equal to 1, I am taking the first term x n, then x star n minus 1. Okay. If you take that correlation, it is just clearly r 1. Second term is n minus 1. Okay, x n minus 1, x star n minus 1, that is r 0, and then x n minus 2. I am just writing the correlation term side by side first. X n minus, next one is a 2 x n minus 2. So, take the x n minus 2, x n minus 2 star, x n minus 2 into x star n minus 2, sorry n minus 1, because k equal to 1 case. So, that will give rise to what? X n minus 2. I can write down, but just for your benefit I am working out those. This is permanently n minus 1. In the summation, this next term I am considering a 2 x n minus 2. So, the term is x n minus 2, x n minus 2 star x n minus 1. If you take the expected value, what you get is simple correlation for the lag n minus 1 minus of this, right. So, what is that? R star 1. Okay. R star minus 1. If you call this index m, I mean whatever the index, then this minus this, n minus 2 minus within bracket n minus 1. So, there is minus 1. Then R star minus 2 dot 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 R star, when last term if you take, this is equal to what? X n minus p, that times x star n minus k n minus 1. So, this will be minus of p minus 1. Okay. and I put it in this kind of form 1 A1 A2 dot 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 AP, that is equal to this row times this column, that is 0, because inner product is 0. Okay. Then take k equal to 2 case, k equal to 1, then k equal to 2. What happens in k equal to 2 case? In the k equal to 2 case, okay, I have got about 5 minutes left. So, I just will develop this equation and call off today. K equal to 2 case, for k equal to 2, what do we have? Same thing, I mean, just instead of, just here we have x star n minus 2. So, this becomes R 2 R 1 x n into x star n minus 2, that gives rise to R 2. The next one is A 1 x n minus 1 x star n minus 2, that will give rise to R 1 times A 1, then R 0, and this will continue. We so on and so forth. Okay. What is the last for k equal to p case? For k equal to p case, that will be R p minus 1 dot dot dot, here will be R 0. These are all zeros. So, you see you get a set of equations. Whether you are doing air modeling or linear prediction, you will get the same solution, because I am only using the orthogonality between E n and x n minus 1 up to x n minus p, which is valid in both cases. So, the equation is valid, this equation is valid for both the cases. Okay. How to solve the equation? Actually, right hand side is all 0, but do not think that this equation is like A x equal to 0 means x equal to 0, because top coefficient here is 1. So, 1 into R 1, that you have to take to the right hand side. So, A 1 into R 0, A 2 into R 1, R minus 1 star dot dot dot, you get one side, R 1 into 1, that goes to the right hand side. Similarly, from the second equation also, R 2 into 1, R 2, that goes to the right hand side. Okay, unknown quantities A 1 to A p, they remain on the left hand side, you solve it. I am just writing in this kind of form. Okay. But these equation, I mean, solving this, there, there are excellent techniques to solve these equations, and there is a famous algorithm called Levinson-Darwin algorithm. This equation actually is called, maybe I just modified little bit, just a few lines. What we have, suppose I started at k equal to 1, but suppose I do this E n x n minus k, and I also take k equal to 0 case, k say equal to 0, that case I take. This is no longer orthogonal, E n is orthogonal to x n minus 1 up to x n minus p, this is not orthogonal, then what it is? This will be what? What is x n minus k? X n minus k has got two components and their summation. What is one component? One component is the projection, okay, k equal to 0. So, for the time being I can put k equal to 0 actually, there is no point in keeping a k here. So, same here, you do not have any k. Another is E n itself, projection and the error together forms x star n. X n, you are putting a star, you are putting a star. Okay. Now, you see E n out of this is orthogonal to x cap n, because x cap n belongs to the past. So, what results is E of expected value of E n into E star n, that is E of mod E n square, which is the error variance, sigma, we call it, actually I will put a notation, I will explain later, it is called forward prediction, because I am predicting x n from the past. So, from past into future it is called forward prediction, and order p, pth order prediction or pth order modeling. So, sigma p f square. Okay, this is just a notation, okay, it is a constant. Now, if you really replace here E n by that expression x n plus a 1 x n minus 1 plus dot 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 up to a p x n minus p and carry out this product, you will see you get this term R 0, because x n into x star n, that gives us to R 0, then R 1 R 2 dot 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 up to r minus p star, and this product will give rise to this term sigma p f square. So, how to solve this equation? First forget about the first row, because right hand side top quantity sigma f square is also unknown, because only thing I know is the data, its correlation values r 0, r 1, r 2. I do not know sigma p f square, there is the variance of that input noise or input white sequence. So, you take from the second row onwards, solve it, whatever value for a 1 up to a p you get, put it here, then take the product between first row and this column, that gives you sigma p f square. This equation is called U lower order equation. In the next class, I will be considering first algorithm to solve this U lower order equations. Okay, thank you very much. Okay, so yesterday we are considering this autoregressive modeling. There is a small mistake I made which I want to correct. Actually, so let me redo it again, because I do not remember exactly where it was. So, let us just redo it. We had a model like this, x n plus summation a I x n minus I equal to say 1 to p. Say pth order model is say E n. Okay. In the case of autoregressive modeling, E n is a white sequence, maybe 0 mean white sequence, and it is a pth order model. It is an all pole model. If you take the Z transform, find out the transfer function, it is only poles. Alternatively, you have also shown that even if there is no such model, you want to just project, you want to just predict x n linearly from its past p values, x n minus 1 to x n minus p, and then x n, and let the prediction coefficients be minus a I, then the error will be what you see here on the left hand side, and that error, then also you have got a similar equation. So, both linear prediction and error modeling give rise to same equation. Further, if it is linear prediction, we know E n is orthogonal, that is uncorrelated with the past p samples, because what we are doing is we are projecting x of n orthogonally on the space spanned by the past p samples x n minus 1 up to x n minus p, and the error then, because it is orthogonal projection, the error will be orthogonal to the total plane or total space spanned by x n minus 1 up to x n minus p. So, E n is orthogonal to the past p values. Similarly, in the case of error modeling, I have seen yesterday that input E n, which is a white sequence, because the model is causal and all that, E n is orthogonal to all the past samples of x n, and therefore, the past p samples also. Since in the modeling problem where we will be estimating or finding out AIs, unknown AIs from the given data, we will be using only the orthogonality between E n and the past p samples. It does not matter whether you are solving a linear prediction problem or error modeling problem, you will get the same set of equations and same solutions. Okay. Now, there we said that how to find out these equations. We know this orthogonality E of, this is what we did yesterday, and then I made a small mistake. So, I am redoing in this step. Say x star n minus k, that is equal to 0.